Welcome to The Explainer. Today, we're diving into a seriously mind-bending mechanical paradox about some of the world's most formidable machines. Picture this. You're standing at the helm of an absolute titan of the ocean. You're commanding a vessel that completely defies scale, slicing through the open water at a crisp 30 knots. But then, suddenly a situation pops up ahead of you, and you need to back this colossal structure up. You reach down for the gear lever to throw it into reverse, but there is a glaring, frankly terrifying problem. There isn't one. That's right, there is literally no reverse gear. None. It sounds like a total engineering nightmare, doesn't it? I mean, how on earth can we build our greatest, most powerful machines without a fundamental way to go backward? Okay, let's dive into this because the scale here is just wild. We are talking about piloting a 400-meter steel mountain. These are the undisputed giants of the sea, carrying upwards of 200,000 tons of cargo, steel, and fuel. To put that into perspective, you're basically trying to steer a horizontally laid-out skyscraper through the ocean. And moving 200,000 tons of mass at 30 knots, that generates an almost unfathomable amount of forward momentum. Every single mechanical component on this ship is under immense, constant stress just to keep the whole thing moving forward. Which brings us to the ultimate question. If these massive ships lack a reverse gear entirely, how do they manage to back up? How do you maneuver or park a skyscraper-sized vessel at a busy port without the ability to just shift into reverse? That is the central engineering mystery we're unraveling today. And as you'll see, solving this problem required engineers to completely throw out the rulebook of traditional mechanics and totally rethink how power is transferred from an engine to a propeller. Section 1. Why gears would shatter. We're talking about the absolute limits of mechanical physics here. You see, in the world of mega engineering, what works for our daily commute is actually a physical impossibility at the scale of the maritime world. Think about your standard car. When you're driving, power travels safely from the engine through a mechanical clutch and into a transmission before finally hitting the wheels. And, it works perfectly. But let's scale that up to a Triple E class ship. On these vessels, the engine alone is as tall as a 4-story building. If you wanted to use a traditional mechanical clutch and gearbox to handle hundreds of thousands of horsepower, that transmission would literally have to be the size of a house. So, obviously, a house-sized transmission is a terrible idea. But why exactly? Well, it comes down to friction. The sheer mechanical friction generated by hundreds of thousands of horsepower shifting gears would be totally catastrophic. The heat and the torque would be so incredibly extreme that it would twist a massive solid steel crankshaft like it was a soft pretzel. Engineers were basically faced with a stark choice. Either build a traditional gear system that would inevitably shatter under its own power, or find a genius, entirely new workaround. That brings us to Section 2, the electric flip. This is all about that produce and consume logic. If mechanical connections are just doomed to shatter, engineers needed a way to transfer all that massive power without any physical gears actually touching. To do this, the maritime industry borrowed a pretty brilliant trick from heavy earth-moving equipment. Look at the Liebherr T284 mining truck, for example. It boasts a staggering 3,600 horsepower, but it sends absolutely zero mechanical power to its wheels. It completely abandons mechanical connections in favor of pure electrons to manage all that force. And many large ships have adopted this exact same produce and consume logic to solve their missing reverse gear problem. And this brilliantly illustrates exactly how that system, which is known as diesel-electric propulsion, works. Step 1, a massive V20-style engine fires up, but it doesn't turn a drive shaft. Instead, it turns an alternator. Step 2, that alternator creates an incredible amount of alternating current, or AC power. Step 3, thick cables safely send this electrical power all the way to the back of the ship. And finally, Step 4, electric motors sitting right on the propeller use that current to drive the ship forward. Notice what's missing here? No gearbox, no mechanical transmission at all. So how do they go backward with this setup? Honestly, it is stunningly elegant. To go in reverse, the captain doesn't have to yank on a heavy mechanical gear. They simply flip the electrical polarity. By reversing the flow of electricity, the electric motors on the propeller instantly spin in the opposite direction. It operates exactly the same way a modern electric car slows down. It uses electromagnetic resistance instead of physical heat-generating friction. It's really a frictionless, gearless masterpiece of engineering. Now for Section 3, restarting the heart backward. Let's look at the direct drive ceremony. But what about the massive giants that don't use electric motors? For ships that rely purely on direct drive combustion power, meaning they turn the propeller shaft directly, the solution is a highly counterintuitive mechanical ceremony. Step 1, you literally have to stop the massive 4-story engine completely. Dead stop. Step 2, the camshaft, which is basically the mechanical brain of the engine telling it when to fire, physically shifts its position. Step 3, this shift forces the engine's valves to open and close in reverse order. And finally, step 4, the crew uses massive blasts of compressed air to literally kickstart the combustion engine so it runs backward. I absolutely love this quote from the source material. It says, "It's like trying to hold your left ear with your right hand. It feels wrong, but for a 100,000-ton ship, it's the most efficient way to survive." Actually, try doing that right now. Reach over your head and grab your opposite ear. It feels completely unnatural, right? But that is exactly what this direct drive ceremony is. Intentionally stalling a massive engine and forcing it to run backward is completely unnatural to how we normally think about machines. But at this staggering scale, it's the brilliant workaround required to survive the laws of physics. Section 4, the crash stop, dissipating all that kinetic energy. Okay, I know what you're thinking. Restarting a giant engine backward sounds like a really slow, methodical ceremony. What happens if there's a sudden emergency right in front of the ship? How do you execute a sudden halt? Well, this brings us to the crash stop. It's the extreme maritime maneuver required to balance immense momentum and dissipate massive kinetic energy over miles just to halt the ship. Because when you are moving hundreds of thousands of tons of mass, you simply cannot just slam on the brakes. The physics of momentum simply won't allow it. It's all about balance and resistance. Think of the Airbus A380 in the sky. It uses a specialized trim tank to actively balance 256 tons of fuel as it flies. Massive ships face a very similar balancing act with their immense forward momentum. In a crash stop, even if the captain successfully flips the polarity or restarts the engine to throw full power astern, which is just nautical speak for backward, it isn't nearly enough to stop the ship quickly. The propeller spinning backward is only part of the solution. The reality is, the ship actually relies on the dense water resistance of the ocean itself to do most of the heavy lifting. The ship essentially drags itself against the water, dissipating all that kinetic energy over several miles before it finally comes to a halt. And honestly, that brings us to the core takeaway for this explainer. The effort of industrial technology to be efficient while struggling with these massive physics problems is truly incredible. Whether it's an airplane utilizing the thin air of the upper atmosphere to flush a cabin toilet, or a 200,000-ton ship literally restarting its own mechanical heart in reverse, these absolute giants of engineering prove a profound point. The most clever solutions don't come from brute force. They come from working with nature, using electromagnetic fields, compressed air, and water resistance rather than fighting against it. It's just so fascinating how the limitations of physics force us to be endlessly creative, from ditching gears entirely for electric fields to forcing engines to run backward. Engineering is basically just applied imagination. So as we wrap up this deep dive into the vanguard of heavy machinery, I want to turn it over to you. What impossible bit of tech should we explore next? What mechanical mystery seems like it breaks the laws of physics but actually relies on a brilliant workaround? Let us know, and maybe we'll decode it in our next explainer.